buffered solutions. These are one of the most important acid-base solutions, and probably the most common example of a buffer solution would be blood. And when we talk about buffered solutions such as blood, they have the ability to resist changes in pH. A buffered solution is a weak acid and a salt of its conjugate base in solution, or a weak base and a salt of its conjugate acid in solution. So if we wanted to look at a buffered solution that's acidic, a good example might be hydrofluoric acid and sodium fluoride in the same solution, because it contains hydrofluoric acid, which is a weak acid, and fluoride ions, which are the conjugate base of that weak acid. And if we wanted to make a buffer solution that was a basic solution, we would use something like ammonia and ammonium chloride, because ammonia is a weak base, and the ammonium ions from the salt is the conjugate acid of that weak base. So let's look at an example of a basic buffer. So here, we want to buffer a solution with a basic pH, so we're going to need a weak base and a salt of its conjugate acid. So let's use ammonia and ammonium chloride as our examples. So we're going to consider a solution containing 0.30 molar ammonia and 0.20 molar ammonium chloride. And the first thing we're going to want to do is talk about what's in the solution. So we're actually going to list them this time. We've got ammonia, which has a Kb value of 1.8 times 10 to the minus 5. We've got our ammonium ion, which has a Ka value of 5.56 times 10 to the minus 10, and we figure that out by taking Kw and dividing it by Kb for ammonia to get Ka. And we know that the Kw for water, since it's in the solution, is 1.0 times 10 to the minus 14. So when we look at all those values, we're going to choose the equilibrium which has the strongest K value. So we're going to start with our ammonia. So we have to think about what the ammonia is going to react with. And in this case, the ammonia is going to react with water. Since ammonia is a base, it's going to accept protons from the water, and its conjugate acid will be the ammonium ion. And what's left over after our water acts like our acid is our hydroxide ion. And now that we've got the reaction, we can go through our steps. So we're going to have our ice chart. The ammonia is originally 0.30 molar. Water we don't have to worry about a concentration for because it's a liquid. Our ammonium ion is 0.20 because it's coming from that ammonium chloride added to the solution. And hydroxide is 0 originally because we're not adding anything to the solution that increases the hydroxide ion concentration. So our reaction is going to proceed towards the right. So X amount of ammonia is going to react. So that's going to give us 0.30 minus X. X amount of ammonium ion is going to be produced. So that's going to give us 0.20 plus X. And X amount of hydroxide is going to be produced. Now we're going to write our K expression, but our K expression is going to be Kb since it's a base. So Kb is going to be the concentration of ammonium times the concentration of hydroxide over the concentration of ammonia, and that equals 1.8 times 10 to the minus 5. So we'll plug in our value. So we're going to get 0.20 plus X times X over 0.30 minus X equals 1.8 times 10 to the minus 5. But since our k value is small, we're going to assume that these x's are insignificant. Now we need to multiply both sides by 0.30, divide both sides by 0.20, and we'll be able to solve for x. So x is going to equal 2.7 times 10 to the minus 5. We can check our 5% rule to make sure that we're okay. So our 5% rule, we want to make sure that x is less than 5% of 0.30. So we're going to take 2.7 times 10 to the minus 5, divide it by 0.30, and multiply it by 100. And that'll give us 0.009%, so we know we're okay with saying x is insignificant. Now, when we solve for x, what we actually solved for isn't the hydrogen ion concentration, but it's the hydroxide ion. So the hydroxide ion is going to be 2.7 times 10 to the minus 5. So I've got two ways that I can calculate my pH. I can either take the negative log of that value and get my pOH and subtract it from 14, or I can take that value and divide it into kW. That'll give me my hydrogen ion concentration, and then I can take the negative log of that. So I'm going to calculate the pOH. So my pOH equals my negative log of 2.7 times 10 to the minus 5, which gives me 4.57, and then I'm going to take 14 minus 4.57, and that's going to give me my pH. So my pH will equal 9.43. So now I know what the pH of this basic buffer solution is, and the next thing I'm going to want to do is see how that solution actually resists changes in pH.